So in the last lecture, we talked a little bit about the theory behind cluster analysis and how to prepare your data and how to estimate k-means cluster analysis. But we didn't say so much about how to interpret and visualize those clusters, and that's what we'll focus on in this lecture. And in particular, we'll look at radar plots, which personally I find really useful for this, and we'll also look at how to map clusters, which will also give us some more mapping skills that you can apply to other problems as well. So let's start by recreating the clusters from the previous lecture. So we saw all this code before. We'll import our libraries, we'll read in the voting data, we'll set index, we'll calculate the Biden percentage vote share, we'll use our list comprehension to get our list of propositions, and then we'll leap over them to calculate percentage yes on each of these propositions. And then we'll flip Prop 22 and Prop 20, where a no vote is more progressive. We'll choose a subset of these columns to analyze. We'll rescale our data. We'll create a new data frame with the scaled version of our data, drop the null values, and then we'll implement our k-means cluster analysis. So initialize the object and then fit it to our data. And we'll add our labels to our data frame. And so we should get the same result as we did before. Yep, remember this cluster 3 was a little smaller, and that's because we used this random state keyword. So how can we best visualize what these clusters mean? Well, if we just had two columns, we could scatter plot with a color code for each cluster. But here we have 10 columns, or 10 dimensions. So let's do our scatter plot matrix again. That could be a first step. The difference is we're going to color code each cluster. So this takes a while, so I ran this in advance. But this is the same Seaborn pair plot with our data frame. The only difference is I'm telling it to color code by cluster ID. What's cluster ID? Well, this is the label that we just added that was produced by our k-means analysis. So we can see that there's these groupings, that this cluster here is low share of Biden votes and also low share of Prop 18 yes votes. So this is one way to visualize the clusters, just with a scatter plot. Personally, I prefer a radar chart. And neither Seaborn nor Matplotlib have this built in, but there is an example in the Matplotlib documentation for how to create a radar chart or a spider or star chart. And so I just copied and pasted that code that you saw in the link. And then I adapted the example, and I put this in a function called radarplot that takes the k-means object that we just estimated and the data frame. So don't worry about the details of this code here. In most cases, especially this function here, I just copied and pasted it from the web. And then this is the example that I adapted from the website. So let's call this function with our data. So I'm calling this radarplot function that I just defined here. So we can see that each cluster, for example, this red one here is cluster 3, is defined by very low scores, very low vote shares on all of these propositions, and even a lower share of voters in this precinct voting for Biden. Before we go further, one thing we might want to do is add the size of each cluster to this legend. So here we just have the cluster names. What if we want to know the size as well? And a hint here is to look at the second to last line of this function where I define these labels. See if you can augment this to add the cluster size. And remember the cluster size we got earlier with this group by cluster ID size syntax. So pause the video here, see if you can figure that out. So what did I do? Well, I stored our cluster sizes that we created above in this new series called C-sizes. Then I'm going to store the number of clusters in a variable k. This is just for convenience. Now I'm going to loop over each cluster ID. So range just gives us a counter. So if I have 5 clusters, then this range is going to give us 0, then 1, then 2, then 3, then 4, and it's going to store this counter in this temporary variable kk. Remember, this is a list comprehension, just a little more complicated than the ones we've seen before. And then I'm going to insert both the counter kk and the size of this, which is looked up from this data frame that we created here. Let's just see what this looks like. So for example, the first time around, I'm going to look up the value from cluster 0. Then I'm going to look up the cluster 1 size, and I'm going to insert it into this string here. So cluster 0 should have a size of 858. So before I adapt my function, I'm just going to see if this code works. And yep, I'm going to print the labels, and I get a list with these right labels. So now let's add this into our code above. So rather than labels just for cluster number, I'm going to have labels with the cluster size. Let's run this again. Okay, so here, rather than just a cluster number, I'm adding the more extensive cluster label into this legend. One interesting substantive finding from this analysis is that all of these clusters form concentric circles. So we're going outwards, right, from very kind of pro-Trump and anti most of these propositions precincts, to then as we go out, they're getting more pro-Biden, but they're also getting more progressive on all of these clusters. There isn't a cluster of precincts that, say, is very anti-Biden, but is much more likely to vote yes on one of these precincts. We might be able to find these types of clusters if we increase k, so we get more clusters, but then we're going to find out that these weird clusters have very few precincts. So if we try it with k equals 10, well, let's drop our old cluster ID column, and then run the same code as we did before, just with n clusters equals 10 rather than as 5. So we see I have lots more clusters, but most of these just have like 12 or 13 or 15 observations. So for example, this blue cluster here, it's voting no for Biden, but it's voting the most support for Proposition 19. But there's only 12 precincts in all of LA County in this cluster. So perhaps this is interesting. Perhaps this is something you want to follow up and understand who these voters are and why they have this collection of political preferences. But let's, for now, go back to our original 5 clusters, run the same analysis as we had before. Because now I think it might be useful to map these clusters, look where they are in space. We're a statewide database team. This is the website where I download the precinct vote data. They also give us a shapefile with precinct boundaries, which I put in your GitHub repository. So let's read this shapefile in using our GeoPandas read file function. This is the name of the shapefile. So for each SR precinct, we get just a geometry, a polygon and a multi-polygon. And note that there's no projection file. If you look in this folder in your GitHub repository, there's not going to be a PRJ file. So GeoPandas doesn't know what the coordinate reference system is. I mean, it's actually none here. If you look at the documentation online, it says it's in lat long. So let's set it to 4326. Remember, 4326 is lat long. Now let's join these polygon boundaries to our voting data. Before we do this, just let's look at the number of rows and whether we can use SRPreq as a unique identifier. This is a standard sort of checks you should do before you join any 2 data frames together. Let's look at the first 5 rows of each. So here we have SR precinct as our index on the voting data. Here it's a regular column, but they look the same. There doesn't seem to be any reason why we can't join them. Let's look at the lengths. We'll have polygons with the boundaries. We have a few more than the voting data. Well, remember we dropped some that were null, so it's not surprising. So perhaps we can do a left join from the polygon boundaries and add the voting data to the boundaries. Let's check if both are unique. Well, they are. The index, which is our SR precinct, is unique on the voting data, and our polygon boundaries are also unique. And that makes it easier. We're going to have a one-to-one join rather than have to worry about duplicating precincts if we have a one-to-many, or even worse, a many-to-many, which may create some unexpected consequences. So now we can join the join. This is just to do the join, a tabular join. Let's set our index on our polygons to SR precinct in place. As join, remember the default is a left join, so let's join from the polygons to our voting data. And the first 5 rows, that looks like everything worked. Here we have our polygons that didn't have any votes, and so this is just going to be null. Now let's map the clusters. The difference here, we're going to color code by cluster ID. So let's initialize our plot, and let's plot our join data frame. Let's convert it to Web Mercator, the same as the base maps, and then let's plot this cluster ID column. Let's add a legend, plot it on this axis object that we just created here, and let's add some transparency in case they overlap. Let's add our base map, and then we can drop the outlying parts of the county and the axis ticks and labels as we did before. Okay, so this is a start, right? That we can see there's a clear geographic pattern to voting behavior in Los Angeles County in terms of these clusters. Well, what can we do to improve this map? One thing we might want is a different base map. Here we used the Stamen Toner Lite, but that's just one of the providers, which we can look at with the CTX providers. So explore these, Google these. Some of them you might think these are you might know what you want. If you want to map railroads, maybe you want to use Open Railway Map. If you are interested in the weather, there's an Open Weather Map, base map. So all these are options that you might want to try and experiment with. But I'd like you to pause the video here and think how else you could improve the map. First of all, make a list of the improvements that you'd want to make. How can you do better from the start? And secondly, if you can, how would you implement some of these changes? Well, there's no right answer here, but what would I do? Well, first I'd replace the missing data with an explicit no data label, so we can distinguish what we have from our clusters with where we just don't have any votes. To do that, we'll actually let's look at our cluster ID right now. So we have an NAN, which isn't being plotted. So to do that, first of all, I'm going to turn this float into a string. Then I'm going to replace the point zeros with an empty string. And then I'm going to replace what is an NAN string with no data. So this just makes it a little more interpretable in the legend. Okay, and you see this is much more amenable to a legend. In the plot itself, some of the things I might want to do. Well, first of all, we had a color bar, which is great for continuous data, but here we have discrete categories, 0 to 5 plus no data, rather than a continuous variable. We can use the categorical equals true keyword argument to get a legend box rather than a color bar. You might want to add a title for the legend. We might want to specify the colors. And I find this Color Brewer 2 website really useful in finding color schemes that are, for example, colorblind friendly or print friendly. And then we can specify a gray for missing data. And a grayscale color is a string between 0 and 1, where 0 is black, 1 is white, and then all other values are in between. So what did I do here? We're getting the colors into a color map. It's a little complicated. I used the example from the Stack Overflow posting. And these are the hex values that I got from Color Brewer 2. And then this last one is a grayscale. So this is a kind of medium gray that I'm going to use for the no data value. Otherwise, everything is pretty similar to what we had before, creating our empty Thig and Axe objects. I'm going to plot the cluster ID. I'm going to add the categorical equals true keyword argument, and this is because of our discrete categories. Then I'm going to pass this CMap object, which I created here, to the plot function. And I'm going to ask for a legend in the upper left, and I'm going to add a title to the legend. And everything else is the same as it was before. I'm going to use the Toner Light base map, but you might find a better base map that you prefer. So we can see this is, first of all, I prefer the color scheme. And secondly, rather than a color bar, we have this legend. Maybe it's a little too big. Maybe I had too much of a font size, but, well, we can change that, right? Let's change this to a font size of 7. And so we can gradually, oops, that only changed the title rather than the fonts, but so be it. But there's other improvements that I'm sure you can make to your map. So the key takeaways I'd like to leave you with from this lecture. Even if the clusters are pretty unsurprising or self-explanatory, in this case they were ordered by ideology, they can still be useful. And in our case, we showed that LA voting is pretty consistently ideological. Your vote on Biden is a really good predictor of the precinct's vote on these propositions. Radar plots and maps are two good ways to visualize that then help you interpret these clusters. And they can also be a starting point for future quantitative research. You can imagine trying to regress the cluster number on some other variables to see what explains voting at the precinct level. But perhaps more usefully, you could do some qualitative analysis. You can use the cluster analysis to find the precinct that's closest to the cluster center, and then do some case studies. You could do the same if you're clustering transit agencies or cities. You can find the city or the transit agency that is most representative of each cluster, and then if you have 5 clusters, do 5 case studies. So cluster analysis can be a launch pad for these other research methods, as well as interesting in its own right. Let's leave it there, and in the next lecture, we'll think about how to cluster in a spatial setting.